Hello and welcome to Declassified Life. Consider a tiny creature with no formal math training, the honeybee. Yet this creature has perfectly solved one of engineering's most complex problems, creating maximum storage area with the minimum use of material. This is the honeycomb, the hexagonal form. Why not a circle? Why not a square or a triangle? This is a mathematical mystery known as the isoperimetric inequality that has puzzled scientists for millennia. Today, we declassify the secret behind this wonder of nature, the Honeycomb Conjecture, and how the bees calculate it. Why do bees build hexagons? The simple answer is efficiency. The bee has two primary goals. One, maximum space to hold honey, and two, minimal use of wax, building material. Producing beeswax is an incredibly energy-intensive process for bees. It takes about 8 kilograms of honey to produce 1 kilogram of wax. The engineering question is, how do we get the most volume while keeping the perimeter of the walls to a minimum within a given area? Let's delve deeper into why the bees discard other geometric shapes. We compared the 4 shapes: circle, square, triangle, and hexagon. The circle encloses the most area, but it cannot tile a plane without leaving gaps. These gaps mean dead space, filled with air that must be heated within the hive, a fatal energy waste in winter. Squares and equilateral triangles tile perfectly, but there's a mathematical catch: corners. A square has 4, a triangle has 3. While a hexagon has 6 corners, when they interlock, 3 different cells share every wall. In squares and triangles, walls are only shared between 2 cells. Because the hexagon has the minimum number of corner intersections, it yields the shortest perimeter and thus the least wax consumption. This results in up to a 15% saving in beeswax per unit of storage area for the bee. The bee's choice is not an accident. This phenomenon puzzled mathematicians for thousands of years. In the 17th century, the famous astronomer Johannes Kepler first proposed that the hexagon was the most efficient shape, but he couldn't prove it. This became known as the Honeycomb Conjecture. It wasn't definitively proven until 1999. Thomas Hales and his team at Yale had to submit a complex 250-page computer-assisted proof over 4 years to finally confirm the conjecture. This proof showed that the hexagon is the absolute most efficient way to partition a surface into equal volume parts, not just for beehives. Hales' proof solidified that a simple natural phenomenon is rooted in a profound mathematical truth. Bees don't use trigonometry to construct this perfect hexagon. What they use is thermodynamics and pressure. Initially, bees build cells that are circular and slightly irregular. Then, hundreds of bees raise the temperature inside the hive above 35 degrees Celsius. The beeswax softens. The soft wax in adjacent cells, driven by surface tension and equal thermal pressure from the inside of each cell, pushes against its neighbors. Just like soap bubbles naturally form hexagonal boundary lines when packed together, the cells are squeezed into the hexagonal form, which requires the least energy and the most balanced force. This is a striking example of biomimicry, where creatures let physics do the engineering. The hexagon's secret continues not just on the flat plane, but also in the cell's 3-dimensional base. If you look closely at the base of a honeycomb cell, you'll see it's not flat, but a pyramid formed by 3 rhombuses. This pyramid saves material at the base of the cell while harboring another incredible engineering secret. this base actually supports the bottom of the comb cell directly opposite it. Bees construct this pyramid at an angle of approximately 109 degrees, which allows the double-sided comb structure to interlock, achieving maximum load-bearing capacity with minimum material usage. The hexagon is nature's most efficient, lightest, and strongest structure, and humans call this biomimicry. We use this structure in snowflakes, turtle shells, and even the massive mirrors of the James Webb Space Telescope. So, what are the most critical engineering applications? 1. Aerospace and automotive. The hexagonal comb structure is used to create sandwich panels by being compressed between two outer layers. These panels are used in aircraft wings and bodies. Why? Because they use up to 90% less weight than a solid material while achieving the same strength. This drastically reduces the fuel consumption and weight of aircraft. 2. Carbon and graphene. The world's strongest known material, graphene, is a single layer of carbon atoms, and its structure is perfectly hexagonal tiling. Here, the power of the hexagon descends to the atomic level. 3. The future and battery packaging. Hexagonal geometry not only saves material, but also optimizes storage space. When electric vehicle battery cells are packaged hexagonally, the empty space between them is minimized, allowing the car to store significantly more energy. In short, nature's simple form continues to dominate the engineering solutions of the future. In summary, the bee's hexagonal structure is not an accidental work of art, but a profound lesson delivered by the laws of thermodynamics through tiny creatures. Bees don't know math, but they apply physics. What do you think is the most impressive engineering feat in nature? Let's discuss it in the comments. In our next video, Declassified Life will continue to declassify the amazing scientific truths hidden in plain sight. Don't forget to subscribe.